Welcome to our review topic of law of sines and cosines. Some of you might be thinking, I don't know how much of a review this is, but you probably have done at least law of sines in science, and you might have done law of sines and cosines in honors geometry or in geometry, and maybe we haven't revisited it in a while, or you need some more clarification. So there might be a few new topics in this lesson, but overall, this is stuff that you probably have seen in the past. So here's where this topic fits into your study of trigonometry. Up to now, you have learned techniques for solving right triangles. But what happens when you want to know information about the sides and angles of oblique triangles? That vocabulary word implies triangles that do not have a right triangle. So we've done SOHCAHTOA. We've done the sine of something equals opposite over hypotenuse. We've used different techniques to find different pieces of information, but they've all had a 90-degree angle in them. You can use law of sines and cosines today on right triangles, but what we're learning today is general for all triangles. In order to solve an oblique triangle, you do have to know at least one measurement of one side, and then any two measurements of the other parts of the triangle. Once you have those three total pieces of information, you have to determine or memorize or whatever the case may be, that if you're given two angles in any side, you're going to use the law of sines. Now you'll see the second bullet underneath talks about the SSA case, in other words, the AS case if you spell it backwards. That is the ambiguous case, and we will discuss that in class. But here is your law of sines. Little a, b, and c represent the lengths of the sides of the triangle. Big A, big B, and capital C, they all represent the angles of that triangle. It doesn't really make a difference what kind of triangle you draw and where you draw those letters, as long as you're putting the capital letter angle A opposite the side of length A. It is a proportion. So you don't have to do A over sine of A equals B over sine of B. You could do the sine of A over little a equals the sine of C over little c. It is a proportion, and you can only solve one proportion at a time. And we'll exemplify that a little bit later in a problem that we're going to do. On the right-hand side, you will see that we are going to talk about the law of sines and cosines if you're given three sides of the triangle or a side angle side case. And when you look at the law of cosines, you're thinking, holy cow, I've got three different formulas to solve. If you notice, they all start out like Pythagorean theorem. Let's look at the top example. It's a squared equals b squared plus c squared. It starts out like Pythagorean theorem. Then you have to subtract off 2 times the product of little b and c, which are the two sides on the right side of the equals. And then you're going to multiply that by the cosine of A, and notice that capital A corresponds to the little a squared that was on the outside. So when you look at that pattern, and I'll talk through that in an example on how I remember that, that's when we use the law of cosines. Now at this time, what's going to make this video a little bit longer is that I've embedded 2 YouTube videos that have the proof of law of sines and the proof of the law of cosines. So if you have about an extra 15 to 17 minutes, just sit back, get some popcorn, watch them. If not, fast forward through this video.
I will now do a proof of the law of sines. So let me draw an arbitrary triangle. Let's see, that's one side right there. And then I get another side here, and I'll try to make it look a little strange so you realize it can apply to any triangle. And let's say we know the following information. We know this angle. Well, actually, I'm not going to say what we know or don't know, but the law of sines is just a relationship between different angles and different sides. So let's say that this angle right here is alpha. This side here is A. The length here is A. Let's say that this side here is beta, and that the length here is B. Right? Beta is just B with a long end there. So let's see if we can find a relationship that connects A and B and alpha and beta. So what can we do? So let me draw, and hopefully that relationship we find will be the law of sines. Otherwise, I would have to rename this video. So let me draw an altitude here. So I think that's the proper term. So if I just draw a line from this side, coming straight down, and it's going to be perpendicular to this bottom side, which I haven't labeled, but I'll probably, if I have to label it, probably label it C because that's A and B. And this is going to be a 90-degree angle. This is going to be a 90-degree angle. And I don't know the length of that. I don't know anything about it. All I know is I went from this vertex and I dropped a line that forms a 90 that's perpendicular to this other side. So what can we do with this line? Well, let me just say that it has length x. The length of this line is x. So can we find a relationship between a, the length of this line x, and beta? Well, sure. Let's see. Let me find an appropriate color. Okay, that's, I think, a good color. So what's a relationship for if we look at this angle right here, beta, x is opposite to it, and a is a hypotenuse. If we look at this right triangle right here, right? So what deals with opposite and hypotenuse? Some of you always, whenever we do trigonometry, we should always just write SOHCAHTOA at the top of the page, SOHCAHTOA. So what deals with opposite and hypotenuse? Sine, right? So, and you should probably guess that because I'm proving the law of sines. So let's see, the sine of beta is equal to the opposite over the hypotenuse. So it's equal to this opposite, which is x, over the hypotenuse, which is a in this case. And then if we wanted to solve for x, and I'll just do that because it'll be convenient later, we can multiply both sides of this equation by a, and you get a sine of beta is equal to x. Fair enough. That got us someplace. Well, let's see if we can find a relationship between alpha, b, and x. Well, similarly, if we look at this right triangle, because this is also a right triangle, of course, what deals x here relative to alpha is also the opposite side, and b now is the hypotenuse. So we can also write that sine of alpha, let me do it in a different color. Sine of alpha is equal to opposite over hypotenuse. Opposite over hypotenuse. The opposite is x, and the hypotenuse is b. The hypotenuse is b. And let's solve for x again, just to do it. Multiply both sides by b, and you get b sine of alpha is equal to x. So now what do we have? We have two different ways that we solved for this thing that I dropped down from this side, this x, right? We have a sine of beta is equal to x, and that b sine of alpha is equal to x. Well, if they're both equal to x, then they're both equal to each other. So let me write that down. Let me write that down in a soothing color. So we know that a sine of beta is equal to, right? A sine of beta is equal to x, which is also equal to b sine of theta. B sine of alpha. B sine of alpha. If we divide both sides of this equation by a, what do we get? We get sine of beta, right? Because the a on this side cancels out, is equal to b sine of alpha over a. And if we divide both sides of this equation by b, we get sine of beta over b is equal to sine of beta is equal to sine of alpha over a. So this is the law of sines. The ratio between the sine of beta and its opposite side, and it's the side that it corresponds to, this b, is equal to the ratio of the sine of alpha and its opposite side. And then a lot of times in the books, let's say if this angle was theta and this was c, then they would also write that's also equal to the sine of theta over c. And the proof of adding this here is identical. I mean, we picked b arbitrarily. B is this side. We could have done the exact same thing with theta and c, but instead of dropping the altitude here, we would have had to drop one of the other altitudes, and I think you could figure out that part. But the important thing is we have this ratio, and of course you could have written it. Since it's a ratio, you could flip both sides of the ratio, and you could write it b over the sine of b is equal to a over the sine of alpha. And this is useful because if you know one side at its corresponding angle, the angle opposite it that kind of opens up into that side, and say the other side, then you could figure out the angle that opens up into it. Or, I mean, well, you could if you know three of these things, you can figure out the fourth, and that's what's useful about the law of sines. So maybe now I will do a few law of sines word problems. I'll see you in the next video. In the last video, we had a word problem where we essentially had to figure out the sides of a triangle, but instead of just being able to do the Pythagorean theorem and because it was a right triangle, it was just kind of a normal triangle, and it wasn't a right triangle, and we just kind of chugged through it using SOHCAHTOA and just our very simple trig functions, and we got to the right answer. What I want to do now is introduce you to something called the law of cosines, which we essentially proved in the last video, but I want to kind of prove it in a more, without the word problem getting in the way. And I want to show you, once you know the law of cosines, you can then apply it to a problem like we did in the past, and you'll do it faster. I have a bit of a mixed opinion about it, because I'm not a big fan of memorizing things. When you're 40 years old, you probably won't have the law of cosine still memorized. But if you have that ability to start with the trig functions and just move forward, then you'll always be set. And I'd be impressed if you're still doing trig at 40, but who knows? So let's go and let's see what this law of cosines is all about. So let's say that I know this angle theta. I know this angle theta, and I know, let's call this side, I don't know, A. Let's call this side B. I'm being a little arbitrary here. Let's call that. Oh, actually, let me stay in the colors of the side. So that let's call that B, and let's call this C, and then let's call this side A. So if this was a right triangle, then we could have used the Pythagorean theorem somehow, but now we can't. So what do we do? So we know A. Well, let's assume that we know B, we know C, we know theta, and then we want to solve for A. But in general, we can, if as long as you know three of these, you can solve for the fourth. And once you know the law of cosines, so how can we do it? Well, we're going to do it the exact same way we did that last problem. We can drop a line here to make. Oh my God, that's messy. I thought I was using the line tool. Edit, undo, undo. So I can drop a line like that. I'm trying to make it. So I have two right angles. And then once I have right triangles, then now I can start to use trig functions and Pythagorean theorem, etc., etc. So let's see. So this is a right angle, and this is a right angle. So what is this side here? What is? Let me pick another color. I'm probably going to get too involved with all of the colors, but it's for your improvement. So what is this side here? What is the length of that side? That purple side? Well, that purple side is just, we use SOHCAHTOA. It's good to write SOHCAHTOA up here. SOHCAHTOA. So this purple side is adjacent to theta, and then this blue or mauve side, B, is the hypotenuse, right, of this right triangle. So we know that. Actually, I'm going to stick to one color because it'll take me forever if I keep switching colors. We know that cosine of theta. Let's call this side. Let's call this kind of subside. Let's call this, I don't know. Let's call this D, side D. We know that cosine of theta is equal to D over B, right? And we know B. Or that D is equal to what? It equals B cosine theta. Now let's call this side E, right here. E. Well, what's E? Well, E is this whole C side. Oh, that's interesting. This whole C side minus this D side, right? So E is equal to C minus D. We just solved for D. So side E is equal to C minus B cosine of theta. B cosine of theta. So that's E. We got E out of the way. And what's this magenta side going to be? Well, let's call this magenta. Let's call it M for magenta. M. Well, M is opposite to theta, and so if we what involves, well, we know it, we've solved for C as well, but we know B, and B is simple. So what relationship gives us M over B, or involves the opposite and the hypotenuse? Well, that's sine, opposite over hypotenuse. So we know that m over b is equal to sine of theta. We know that, let me go here, m over b, right, because it's the hypotenuse, is equal to sine of theta, or that m is equal to b sine of theta, right? So we figured out m, we figured out e, and now we want to figure out a. And this should jump out at you. We have two sides of a right triangle, and we want to figure out the hypotenuse. We can use the Pythagorean theorem. This Pythagorean theorem tells us a squared is equal to m squared plus e squared, right? Just the square of the other two sides. Well, what's m squared plus e squared? Let me switch to another color just to be arbitrary. So a squared is equal to m squared. M is b sine of theta, so it's b sine of theta squared plus e squared. Well, e we figured out is this. So it's plus c minus b cosine theta squared. Now let's just chug through some algebra. So that equals b sine b squared sine squared theta. Sine squared theta just means sine of theta squared, right? Plus, and then we just FOIL this out. Although I don't like using FOIL, I just multiply it out. But c squared minus 2cb cosine theta plus b squared cosine theta. Right? I just expanded this out by multiplying it out. And now let's see if we can do anything interesting. Well, if we take this term and this term, we get that those two terms are b squared sine squared of theta plus b squared cosine. There should be a squared there, right? Because we squared it. B squared cosine squared of theta, and then we have plus c squared minus 2bc cosine theta. Well, what does this simplify to? Well, this is the same thing as this equals b squared times a sine squared theta plus cosine squared of theta. Something should be jumping out at you. And then that's plus c squared minus 2bc cosine of theta. Well, this thing, sine squared plus cosine squared of any angle is 1. That's one of the early identities. That's just, that's a Pythagorean identity right there. So this equals 1. So then we're left with, going back to my original color, we're almost there. A squared is equal to, this term just becomes 1, so b squared, we're just left with a b squared, right? Plus c squared minus 2bc cosine of theta. That's pretty neat. And this is called the law of cosines. And it's useful because, if you know an angle and two of the sides of any triangle, you can now solve for the other side. Or really, if you want to, if you know three sides of a triangle, you can now solve for any angle. So that also is very useful. The only reason why I'm a little bit, here or there is it is good. If you are in trigonometry right now and you might have a test, you should memorize this because it'll make you faster and you'll get the answer right quicker. I'm not a big fan of just memorizing it without knowing where it came from, because a year from now or 2 years from now, when you go to college and it's been 4 years since you took trigonometry, you probably won't have this memorized. And if you face a trig problem all of a sudden, it's good to kind of get there from scratch. But with that said, this is a law of cosines, and if you use the law of cosines, you could have done that problem we just did a lot faster, because you just have to set up the triangle and then just substitute into this, and you could have solved for A in that ship off course problem. I'll see you in the next video.
Before we start this example, I just want to remind you, since this is our first video of the year, that you may mute me if you would like to try the problem yourself. you can work along with me. You should be taking notes and writing what it is that you need down to understand the new learning. And you can also stop and rewind me if there is something you didn't get the first time. So please make sure that you use those computer tools. All right, so here's example 1. This is the information I'm given in a problem. I drew an obtuse triangle because I noticed that angle C is 102.3 degrees. So that's going to be an obtuse triangle. And the first thing I need to do is I need to mark my picture. So I am going to mark that angle C is 102.3. I'm going to mark that angle B is 28 degrees and 0.7 degrees. Now, little b denotes a side length. So the side length of B is 27.4. So when I look at that information, I am given an angle, I'm given an angle, and I am given a side. And if I refer back, this tells me that I'm going to use, I have angle, angle, side, so this is going to be a law of sines problem. What I need to do now is I need to find the missing information. So the missing information I need to find is going to be the measure of angle A, side C, and little a, side A. The measurement of angle A is pretty straightforward. If you recall the theorem from geometry that the sum of the interior angles of any triangle is 180 degrees, all I did was take 180 degrees, I subtracted 102.3 and 28.7 degrees, which were the angle measurements of C and B, and therefore measure of angle A is 49 degrees. Okay, for angle C, now that I know that A is 49 degrees, I could have used little a and big A. I will just tell you for consistency's sake, in the problem, I was given angle B and then side B. That was the family of either A, B, or C in the triangle that was given. So when I start setting up my proportion, that's what I'm going to do first. So the proportion I set up was side B, 27.4, over sine of 28.7 degrees. That equals C over sine of 102.3 degrees. I cross multiply to yield C sine 28.7 degrees equals 27.4 times the sine of 102.3 degrees. Next, I divide both sides by the sine of 28.7, and when I put that in my calculator, I ended up with 55.75, and that would be a length of side C. Now, I can't do Pythagorean theorem to find angle A. This is not a right triangle. So again, I'm going to go back, and I'm just going to keep using, for consistency's sake, I'm just going to use the B family, but at this point, when I set this up, I did 27.4 over the sine of 28.7 degrees. Those values were already in my calculator. That was the method of my madness. But I could have also used the sine of 102.3 degrees and then the 55.75 degrees that I found. But remember, 55.75 was rounded. So I just try to stay with the given information to stay the most accurate. So then again, I cross multiply, I divide by 28.7, and I yield the measurement of A is 43.06 as its measurement, and that would be in feet. And so we have just solved this triangle using the law of sines. Okay, next, last problem. We're given that side A is 8 feet, B is 19 feet, and C is 14 feet. So I'm going to mark my picture. So A is 8, C is 14, and B is 19. I was given 3 sides. Therefore, this is a law of cosines problem. If you're wondering, this is just kind of review. This is not really a part of the problem. But if you're wondering, why did I draw an obtuse triangle? And that should be and, not and. Okay. Why did I draw that triangle? Well, if you remember from geometry, you had what was called a triangle inequality theorem. And so if I set this up like Pythagorean theorem, 8 squared plus 14 squared is not 19 squared. Therefore, it's not right. But if I do the arithmetic, I notice that the quote-unquote hypotenuse side is bigger. Therefore, it had to be an obtuse triangle. And so I know if I don't get an angle more than 90 degrees for angle B, then maybe I've done something wrong. Okay, I'm going to type a little bit while I do this, just so you can kind of see how I remember this, I'm going to give you a tip. Law of cosines is kind of a pain in the rumpus. It's long, it's laborious, it's a lot of typing in your calculator. I like law of sines better. It's easier for me to cross multiply. I gave you a lot of steps in the previous problem that you probably don't even need. But in order to switch to law of sines later in the problem, which you are allowed to do, you have to find the largest angle first. And that's because you can get an ambiguous case with the law of sines, which, stay tuned, we will learn that next time we come to class. Okay, let's talk about angle B for just a minute. And I'm going to pull up my math type. And I'm going to split this screen. Okay, if I look at my picture here, here is how I remember it. I want to find angle C, or excuse me, angle B. That's what I want to find first. Did I type that in right? I sure did. Okay. We want to find angle B. It's the largest angle because 19 is the largest side, and the largest angle has to be opposite the largest side. So I'm going to start with 19 squared. Okay. That's how I remember it. I want to find angle B. Opposite of angle B is little b, and that's 19. All right, so 19 squared. I remember this starts like Pythagorean theorem. So that's going to be 8 squared plus 14 squared that's going to be minus 2 times 8 times 14 cosine of B. Now, you are more than welcome to type 19 squared in your calculator and simplify 8 squared and do all of that. But here's the one thing that I really want to stress. The 8 squared and the 14 squared are being added together in relationship to the cosine of B. Cosine of B is what I want to get by itself. I am adding the 8 squared, I am adding the 14 squared, and I am multiplying the cosine B by negative 2 times 8 times 14. So in order to get the cosine of B by itself, okay, I'm going to look at that 19 squared, and I have to subtract off the 8 squared. I have to subtract off the 14 squared, and then I have to divide all of that by the negative 2 times, hold on, okay, I have to divide all of that by the negative 2 times 8 times 14. And in order to get B by itself, you can't divide by cosine. You can only take an inverse. So if I take an inverse on this side in order to get B by itself, then I have to take an inverse on this side as well. So what happens next is all of this equals cosine B. That's wrong. Equals B. So now I'm going to type that in my calculator, and I can type it in one step. Okay? So I'm going to hit inverse cosine, making sure that my mode's in degree. So inverse cosine. Okay, and I'm going to put the top in its own parentheses. So 19 squared minus 8 squared minus 14 squared and I'm going to divide that by negative 2 times 8 times 14 and so the measurement of angle 116.8 degrees. Okay, now we're going to go to the measurement of angle C. Now that I know that angle B is 116.8 degrees, I can switch to law of sines because I have the B family. So when I do that, okay, 19 over the sine of 116.8 equals to 14 over the sine of c. So again, let's math type this out. This means that 19 sine c equals 14 the sine of 116.8. I'm going to leave out the degree symbol just for now for the sake of time. Sine of c is going to equal 14 sine of 116.8 all over 19. And again, in order to get rid of the sine, I have to take its inverse. And if I take the inverse on one side, then that means I have to take the inverse on the other. So that means c is going to equal the inverse sine of this expression. Oh, there's my degree symbol. Okay, we'll put it over here. So let's type that in. So I'm going to have the inverse sine. And I'm going to put the numerator in parentheses, 14 sine of, oh, hold on, inverse sine of 14 sine of 116.8 divided by 19. And we get that it is equal to approximately 41.1 degrees. And then to find the measurement of angle A, I can add those up or subtract them from 180. So at this time, you are ready to approach learning opportunity 1. Notice that it's not a ton of problems. It's quality, or quality, not quantity. And if you have any questions, let me know. You will have some time tomorrow in class to work on this assignment, but I